Now, before we go ahead and look at examples of linear transformations and their properties, we need to take a quick moment to be introduced to what are known as the elementary vectors. Now, I want you to note that the columns of the identity matrix are in fact the elementary vectors. So to get us started here, let's think about or consider a 3 by 3 identity matrix. And we denote that 3 by 3 identity matrix as I sub 3. So the columns of the identity matrix I sub 3 are a 3 by 3 identity matrix. So we have the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So the columns of this 3 by 3 identity matrix are the elementary vectors. And we denote them as E sub 1. So this is our first column vector, 1, 0, 0. We have the second elementary column vector, E sub 2, and that's 0, 1, 0. And last but not least, we have our third column vector, our third elementary column vector, defined as 0, 0, 1. And these three vectors are the elementary vectors. So thinking about this graphically, we have space down below. So we have our first elementary vector, E sub 1. So that's the position vector from the origin to the point, 1, 0, 0. So here is our first elementary column vector, E sub 1, at the, or pointing to the ordered triplet, 1, 0, 0. We have our second elementary vector, so the position vector from the origin to that terminal point, 0, 1, 0. So that's our second elementary column vector, 0, 1, 0. And last but not least, we have our third elementary vector, the position vector from the origin pointing to the ordered triplet, 0, 0, 1. So here is our third elementary vector, E sub 3, 0, 0, 1. Now, we can actually use these elementary vectors to decompose an arbitrary vector in space. So, let's go ahead and let some arbitrary vector x be some vector in space, or in R3. And now we can decompose this vector x in R3 using the elementary vectors. So since x is, or vector x is in R3, we know it has three entries, x1, x sub 2, x sub 3. So an alternative way to think about this vector is to break it down into a linear combination. So we have the scalar x sub 1 multiplied by the vector in the x sub 1 direction, 1, 0, 0, plus our scalar x sub 2 multiplied by the column vector pointing in the x sub 2 direction, 0, 1, 0, plus that scalar x sub 3 multiplied by the vector pointing in the x sub 3 direction, 0, 0, 1. And so we can see that these are the three elementary vectors defined above. So we have the linear combination x sub 1 times the elementary vector E sub 1 plus x sub 2 multiplied by the elementary vector E sub 2 plus x sub 3 multiplied by the elementary vector E sub 3. And now we can even take this one step further and think to ourselves, well, we know that a vector equation is equivalent to a matrix equation. So we can rewrite this as the matrix containing these elementary vectors, E sub 1, E sub 2, E sub 3, multiplied by that column vector x with the entries x sub 1, x sub 2, x sub 3 to attain the equivalent matrix equation. So we've actually taken this arbitrary vector x in 3 dimensions and rewritten it as a linear combination to attain the vector equation. And we've taken it one step further and rewritten this vector equation as a matrix equation. And we can see this matrix, this matrix here containing the elementary vectors is the identity matrix in 3 dimensions. So we have the identity matrix I sub 3 multiplied by vector x, which brings us full circle right back to vector x. Woohoo! So these are alternative ways in which we can decompose our vector x. And this doesn't just hold true in R3, it holds true in n dimensions. Now, before we get too excited, let's go ahead and think about a quick, cute example here. A numerical example to really better understand what's going on. So let's consider some vector x in 3 dimensions. We'll do 2, 3, 4. So we again can decompose this column vector into a linear combination of the elementary vectors. So using that vector equation that we defined above, we know that we can rewrite this column vector as the linear combination 2 times elementary vector e sub 1 plus 3 times elementary vector e sub 2 plus 4 times elementary vector e sub 3. Now, to check, to make sure that these are in fact equivalent, let's plug those column vectors in. So this is the same thing as saying 2 multiplied by that column vector 1, 0, 0 plus 3 multiplied by that column vector 0, 1, 0 plus 4 multiplied by the column vector 0, 0, 1. And by vector multiplication, we know that this is equivalent to the column vector 2, 0, 0 plus 0, 3, 0 plus 0, 0, 4. And by vector arithmetic, we have 2 plus 0 leaves us with 2. We have 0 plus 3 plus 0 is 3. And 0 plus 0 plus 4 is 4. Woohoo! So they are, in fact, equivalent. We have confirmed with our numerical example here that these are 2 alternative ways to write this column vector. Now, this is going to be particularly useful when we start working with linear transformations. So let's go ahead now and explore this application with linear transformations.